Good evening, everyone. My name is Gillis Lowry, as you heard. I'm a former student, now researcher at the Carl Sagan Institute here at Cornell University, and next year I'll be a master's student in San Francisco. Before I was a full-time researcher, I actually gave planetarium shows in St. Louis, and at the end of each show, I would ask the audience to look up at all those stars in the sky and wonder how many planets were actually looking back. And we think that on average, there's about one planet for every star in the sky, and maybe 20% of those planets are actually habitable and rocky. So that means that they are the right temperature, that they might have liquid water on their surface, and they're small enough that they could have a rocky surface like the Earth. And with 100 billion stars in the Milky Way, that means chances are pretty high there's something out there. So we found 6,000 exoplanets so far in our search, but once you start to narrow that down to just the ones that are in the habitable zone, that could have liquid water, you have a few hundred. And then when you start to look at just the ones that are around 2 times the size of the Earth or smaller, so they could be rocky, you have just a few dozen. So taking a closer look at these few dozen exoplanets, I plotted about 40 of them up here. You see they range in their type of host star that they go around. Some of them go around stars almost the size of the sun. Some of them go around very small red dwarfs. And they also range in how potentially habitable they might be. Some of them are closer to their star, so they receive a lot more light. Some of them are farther away. They're probably a lot colder. And the stars that are along that green line are a little bit closer to being like the Earth, we think. But we still have had barely any data on the actual atmospheres of these planets. So until we can actually figure out what chemicals are in the atmospheres, what biosignatures might be signs of life, then we won't actually know where the true limits of this habitable zone lie. So if you recall the title of this talk, it is hard to find life on other planets. And the main reasons are these two. Planets, rocky planets, are really small compared to their stars, and all of these planets are very far away. The closest planets to Earth, Proxima Centauri b, those planets are 4 light years away, and 1 light year is 6 trillion miles. Everything else is more than 4 light years, at least dozens or hundreds of light years away. Even though it's hard, though, I'm going to show you some of the methods that we use to discover these planets and then take a look at a few specific cases that we're hoping to get data on very soon. So here's an example of how we actually discover these planets in the first place before we can look at their atmospheres. A planet passes in front of its star. Here I have Earth for comparison, so you can see how truly small the Earth is compared to the sun. So as it passes in front, we see a little bit less light hitting our telescopes because it's blocking that tiny amount of light. So as it does so, we see this dip in starlight, and that tells us that the planet is there. But if we want to actually see the atmosphere, the tiny little skin on top of that planet, we have to be a lot more precise. So what I'm showing you up here is an exaggerated view. The atmospheres normally aren't that big compared to the planet itself. But as the starlight passes through these tiny, tiny atmospheres, it hits a bunch of molecules along the way, a bunch of chemicals. And as it hits those chemicals absorb very specific colors out of the full rainbow. So then when we look at the data we receive, just the tiny little bit of starlight that's actually coming from the atmosphere, we can start to say, okay, we know that water on Earth absorbs these very specific colors out of it. And that means that if we're seeing these little colors gone, absorbed around this exoplanet, it might actually have water. But as I said, these planets, really small, and they're really far away. So in practice, it's really hard to get even any chemicals around any of these planets. So taking a look at that plot from earlier, I've labeled pretty much the only planets we have a good shot at observing the atmospheres of so far. It's just TRAPPIST-1. So if you hear a lot about TRAPPIST-1 in the news, this is why. We basically only have a shot at these ones, and that's because you see they're at the very bottom of the plot. Their star is very small, so in comparison, they take up a lot of their star. So it's a lot easier to detect them. But here's a look at the actual data. Actual data, this is simulated data that I've been working with over the past few months. And this is sort of an idea of the raw data you'd be getting from the telescope. As you can see, there's huge bars that extend from the top to the bottom. And that's just because the planet is so small, it's so noisy, and we're so uncertain in the actual data points that we're getting. But hopefully we can start to reduce this data and actually see where the chemicals are popping out of it. So just an example, these tiny little bumps are where you would actually be seeing the data from these chemicals. Even if you can get something like that, these planets are very close to their star as well, because if they want to be habitable, they have to be very close in to their very cool and small star. So they're much closer than the orbit of Mercury would be in our solar system, just to get as much light as they can. And that means there's a lot of other factors that I haven't thrown in yet. If they're really close to their star, there's a lot more dangerous radiation that they'd be receiving, and it's possible that their star, all that dangerous radiation could also be stripping away their atmospheres. So until we get more data, we're not even sure if these planets have an atmosphere at all, let alone the biosignatures like water and methane that are produced by life on Earth. Yeah, so really, the important takeaway here is just to be skeptical all the time, even if you're a scientist who really wants to find life in your data. So what's the best way to continue to search for aliens and to try to improve our chances of finding them? I would say the biggest reason, and the one that we're always pursuing all the time, is to build bigger and better telescopes just to get bigger and better data. The James Webb Space Telescope has been incredible. It's given us great data, but all those little squiggly lines I was showing you earlier with the huge error bars are simulated James Webb Space Telescope data. So even with the state-of-the-art best telescope we have so far, it's still really hard to detect even our best chances at finding life. So we have a few upcoming observatories and telescopes that should be really promising. We have some on the ground, and hopefully some of these telescopes and observatories will actually be able to get us direct images of rocky exoplanets. What I'm showing you right here is direct images of gas giant exoplanets. These are the only ones we've been able to image so far, and they're very big and they're also pretty young, so they're still very hot. But hopefully some of these observatories in the future will start to take pictures like this of actual rocky planets in the search for life, and then we won't have to wait for these planets to pass in front of their star and try to disentangle all of that from the starlight. So this will be very helpful in the search for life. And then a few other ways just to keep building our same frameworks we've had before, keep inspiring the next generation and teaching them in the methods, and of course to keep funding NASA, because without NASA, much of this would be impossible. For all of you, there's much you can do to help keep NASA's funding, but I also encourage you, like I said, to be skeptical of any big headlines you see about the discovery of life. Chances are there will be many more false positives and boys who cry wolf before we actually find life. Thank you.